looking at how we can understand and use heat capacity, specifically understand how calorimetry can be used to calculate enthalpies of chemical reactions. Okay, so if we're going to be measuring the heat, the easiest way to do that is to measure the temperature of something in the surroundings. If we can capture all the heat that's coming off of a chemical reaction and then measure how much heat, how much the temperature changes, if we know how much, how many degrees in temperature change there will be per joule of heat absorbed, then we can just calculate, we can measure the heat of reaction by looking at a change in temperature. So we need to know heat capacities. What is the relationship between the heat transferred into or out of the system and the temperature? So there's three ways of measuring the same thing, and this can be sort of a pain. So you just have to be very careful when you are looking at your problem, that either in a textbook or in real life, what information you're being given. So the heat capacity, the total heat capacity of the system, the heat absorbed is going to be equal to the heat capacity times delta T. That's if you have the heat capacity for your entire calorimeter or your entire aluminum pan that's heating up. The molar heat capacity, usually capital CM, there the heat absorbed is going to be equal to the number of moles times the molar heat capacity times delta T. And finally, you'll see specific heat, which doesn't say heat capacity. Why specific heat? That's such a bizarre name. Like, I don't know, it's too ambiguous, but it's what's used. Frequently a small c or sometimes a capital C with an S. There would be the heat absorbed is equal to the mass of the object times the specific heat times delta T. So these are all different ways of getting at the same quantity. The best thing to do is look at the units. Obviously, if it's going to be joules per gram Kelvin, then you know it's a specific heat. If it's per moles Kelvin, you know it's a molar heat capacity. And if it's just joules per Kelvin, you know it's a heat capacity. So all you have to do is pay careful attention to the units, and you know which of the three equations to plug it in. All right, so now that we have this concept of the enthalpy, we can think about how we can actually make precise chemical measurements of the enthalpy released in reactions. So a bomb calorimeter is one common calorimeter setup that you'll see. So it measures changes in internal energy for combustion reactions. So what you have here, you can have a little sample down there, provide some oxygen, and that's very tightly sealed with the bomb, and then it has water around it. Have a thermometer, and then you ignite it, watch it burn, and see how much it heats up the water. So the bomb means there's no change in V. So in this case, delta E is equal to Q. The heat you get out is a change in energy. And the way you would calculate that, so the heat coming out, if you keep track of the heat capacity of the entire system, the water plus the sample, then and then calculate measure the change in T of the water. Well, if everything's at equilibrium, it'll be the same. Then you can get the heat out just by measuring the change in temperature. If sometimes it's listed as the heat capacity with heat capacity of the bomb calorimeter without the water. And so what you'd have to do is combine the total heat capacity, which is going to be heat capacity of everything but the water, plus the mass of the water times the specific heat of the water. And a solution here, we'll see in a situation where that's the case, times delta T. So you have the total heat capacity of the whole system, the heat capacity of everything but the water, and then the heat capacity of the water. And the important thing here is that what is the division between system and surroundings? So the system here is the reaction, just the things that are reacting. This is the reaction. The surrounding, everything else is the surroundings. And so the change in heat from the calorimeter is equal to minus the heat given off by the reaction. So that's important to remember to get that minus sign right, or else you might do a calculation and end up showing something's endothermic where it's actually exothermic. So here's a setup that's pretty similar. So we have 1.045 grams calcium oxide added to 50 milliliters of water at 25 degrees C in a bomb calorimeter, a slightly different setup than when we're actually combusting things. The temperature, once we add in the calcium oxide, increases to 28.9 degrees C. What's the delta E of the reaction for calcium oxide plus H2O goes to calcium hydroxide? It'll be aqueous half calcium hydroxide. The calorimeter without water has a heat capacity of 20 joules per degree C. Notice that's a total heat capacity, not per unit mass of the calorimeter or per mole of calorimeter or whatever it's made up of. It's a total heat capacity. And the specific heat of solution is 4.18 joules per gram degree C. Specific heat of solution, we say the specific heat of solution because frequently we can just assume that the solution itself has about the same specific heat of water. If you dissolve a small amount of stuff in water, it will still heat up about the same amount water does. So let's dig in on how we would do this. So the total heat of the calorimeter is going to be, right, that is C delta T. And the total heat capacity is going to be 20 joules degree C for the rest of it other than the water, plus 4.18 joules C per degree C gram. And then that's going to be multiplied by the total mass of the solution, which is 51.045 grams, and then multiplied by 28.9 minus 25 C. And so that ends up being, once we do all the multiplication, add it together, the grams cancel here, we get 233 joules degree C times 3.9 degrees C, and that results in 909 joules. And so that is the Q of the calorimeter. The Q of the system, i.e. the reaction, was minus 909 joules. Okay, so that's the amount of heat that the surrounding absorbed. So how much energy is being given off per mole reaction? We have 1.045 grams calcium oxide. Calcium oxide is 56.08 grams per mole. And so that is 0.01863 moles. So the delta E reaction is just going to be Q and delta E reaction equals minus 0.909 kilojoules divided by 0.01813 63 moles. So it's going to be minus 48.8 kilojoules per mole. Q reaction equals minus the Q calorimeter, or we could just think, well, it's heating up the system. It must be an exothermic reaction. Therefore, the sign is going to be negative. The energy change and energy of the reaction is going to be negative.